Welcome to chemistry in chapter 4, section 1, defining the atom. So here's our lecture notes that we're going to go through today. And one thing I'd like to let you know is that there is a video. You do have to define the two terms that are in this section. You're going to find them as we go through. We'll talk about them. Plus, you're also going to find them at the end of this lecture notes. So let's first of all start about, hey, you get a present. It's wrapped up and you can't see it. Well, how do you know what's inside? Well, I don't think any of you have ever checked presents by shaking them underneath the Christmas tree. Well, you know right away that if it slides back and forth, doesn't make a whole lot of sound, it's probably closed. But if it goes tink tink, we know it's not closed. And that might be a good thing. So we can look at things, how things are wrapped, all these other things that let us know what things are, even though we can't see them. So how can, the people that determined what an atom looked like or what it was, how do they know without being able to see it? And I can tell you right now, Democritus, way back in time, he was a long time ago, and he could not see an atom, but he predicted what an atom might look like. So we're going to talk about early models of the atom, in particular by a person by the name of Democritus and John Dalton. Okay, so let's go ahead and start off with Democritus, or that's the first one we're going to talk about. But let's get that first term. A blank is the smallest particle of an element that retains its identity in a chemical reaction. Well, that is going to be an atom. So an atom is that smallest thing. It's one atom of a particular element. Okay, Democritus says we couldn't break it apart. It was indestructible, but he still didn't know what it looked like. And a lot of it was because they were early philosophers talked about them, but they couldn't observe them. They didn't have the technology like we have now. Okay, so the first person we're going to talk about is Democritus from 460 BC to 370 BC. He was really one of the first ones to suggest the existence of atoms. He might not have been the first one, but he was definitely the first one to write something down and basically pass it along. He reasoned that atoms were indestructible and indivisible, which means that we can't break it apart, we can't destroy it. An atom is the smallest thing. Okay. Since then, we kind of found out he was wrong with that a little bit. Okay. So although his ideas agreed with scientific theories later on, it didn't explain one thing, and that was chemical behavior. Excuse me. So why do atoms behave the way that they behave? That's what we're talking about. So it basically lacked the experimental support. So it lacked the science, in particular the scientific method, something that could be reproduced. So Democritus' idea was kind of widely accepted, but there just wasn't anything to back it up. Okay, it wasn't until, look at the time, 1766 to 1864, so somewhere in the middle there, John Dalton, an English chemist and school teacher, well, he came up with his idea. He using new technology. So using experimental methods, he transformed Democritus' idea into a scientific theory. Later on, that scientific theory is going to be known as Dalton's atomic theory. Okay, he studied the ratios that combined in chemical reactions. So when hydrogen and oxygen got together, he combined the ratios of those, and he made some important discoveries or ideas about those as when he looked at those ratios. So again, his result is known as Dalton's atomic theory, and we're going to go ahead and explain that.
Hey everyone, Professor Davis here, ChemSurvival.com and ChemSurvival. And today I'm going to talk to you about Dalton's atomic theory. Dalton's atomic theory was devised by an English chemist by the name of John Dalton. He was working at the very beginning of the 19th century, and he's actually most famous for his law of partial pressures of gases, but he's also, or he should be, equally famous for being the first scientist to truly use data to support the existence of atoms. Let me show you how he did that. Let's consider two very simple reactions, the likes of which you'll probably encounter in an introductory chemistry course. We can take oxygen and react that with two equivalents of hydrogen to create water. But water is not the only thing we can make from oxygen and hydrogen. If we combine them instead in different proportions, we can create hydrogen peroxide, the likes of which you might find in your medicine cabinet at home. Now, Dalton used reactions like this to demonstrate that there must be a fundamental, indivisible particle which is combining to make these materials. Let's take a look at how he did it. Looking at the top reaction, let's say that I start with 32 grams of oxygen. I'll need 4 grams of hydrogen to completely convert that oxygen into water. And when I measure the amount of water formed, I get exactly 36 grams. Now, you probably noticed that the sum of the masses of all the starting materials in this case is equal to the mass of the products. And this observation will actually hold for any reaction at all, any chemical reaction. Let's take a look at the bottom. 32 grams of oxygen can react with 2 grams of hydrogen, in this case to form 34 grams of hydrogen peroxide. Again, my masses should balance. We call this the law of conservation of mass, because in any chemical process, it will always hold true that the total mass of all starting materials is equal to the total mass of all products. Now let's look at one more mathematical relationship. Let's look at the ratio of the starting materials to one another. In the top reaction, we have 32 grams of oxygen and 4 grams of hydrogen. So I need 8 times as much oxygen as hydrogen by mass. This is something that Dalton could have measured. In my lower reaction, I have 32 grams of oxygen reacting with 2 grams of hydrogen. The ratio, 16. And these ratios are similar to one another. They're divisible by a very small whole number ratio, in this case 2. This is known as the law of multiple proportions, and it holds for a number of reactions in which we combine multiple substances to make more complex molecules, just like we're doing here. What Dalton did was to combine the law of conservation of mass with the law of multiple proportions to demonstrate that there must be some fundamental indivisible particle. In other words, you can't add a half of a hydrogen atom to a molecule. Therefore, you can't have a proportion that isn't either 8 or 16 in this type of reaction. This is what Dalton used to support his theory. And because it was his theory, he got to name these fundamental particles. And he chose the name atom from Greek words meaning not divisible. This is the source of the term that we use today to describe this fundamental unit of matter. That's all for now, everyone. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. I'll see you on my next video.
So let's kind of go over Dalton's atomic theory. He said that all elements are composed of tiny, indivisible particles called atoms. In this case, we have atom A. And we could, if we mix, or if we have them separate, every element has its own atom. And all the atoms are the same for each element. Okay? When we mix them together, we can blend them together. It's still always going to be in a whole number ratio, but when they chemically combine, they're always going to combine in that exact same proportions for that particular compound. In this case, it looks like water. Okay, so what was John Dalton able to study atoms through, even though he could not observe them directly? And what evidence did he use to formulate his atomic theory? Well, what he did is he studied the ratios, if you remember, and how these elements combine in chemical reactions, and he realized that the ratios were always the same. And since we can't give a half of one of these things away, they must be a whole number ratios. Okay, so he observed that atoms mix, they maintain their identity unless they combine in a chemical reaction, and then they come up with a whole different type of identity. Okay, so how was Democritus' idea different from that of Dalton's? Well, if we look at it, Democritus' idea did not explain chemical behavior. It wasn't a scientific theory because it lacked any type of scientific or experimental support. And so using support or science Dalton transformed Democritus' idea from atoms into a scientific theory that explained really chemical behavior. Okay, sizing up atoms. One of the biggest things about sizing up atoms that you need to know is that atoms are extremely small. And what do we use? Well, we use electron microscopes. Now, how did Dalton figure this out? Well, he illustrates the concept with mercury. Now, with mercury, it looks like this, okay? And what you can do is every drop of this mercury has the same properties no matter what size. Even if we continue to break it down into just a speck or a small atom. Same thing with if we took a copper coin. If it's all copper, no matter how small we grind it down, each little speck is going to still have those properties of copper. Okay? And again, even if we go all the way down to the size of an atom, okay, we're going to eventually still have that same chemical properties that you would with a larger piece. And again, finally, even if you get down to the atom, it still has that same chemical properties. So atoms are very small. Well, how small are they? This number right here, atoms can fit into the size of a penny. That's huge. It's more than what the Earth's population is. More than double what the Earth's population is. Okay? It's a huge number. Atoms are extremely small. That's why we need electron microscopes to actually see them. And notice this, 100 million is only a centimeter long. Well, there's 2.5 centimeters in an inch. So it's less than a half an inch. Huge number of atoms that can fit in a small area. Okay, so despite their small size, atoms are observable using scanning electron microscopes. All you have to realize is that they are going to be electron microscopes. But the thing about it is, we can see the atom, but we can't see the parts of the atom, what makes up the atom. So all we see is just kind of the outermost energy level of that particular atom. We have to have it magnified on very high magnification in order to see this. Okay? And matter of fact, we can actually move individual atoms and we can move them around. The problem is if we have to look into a scanning microscope to do this, it's going to take us a long time in order to get any little thing made. But if we look at this and we're able to manipulate at the atomic level, we're going to be able to create things that are extremely small, such as nanocars. Now, again, you don't think of a nanocar as being something that's that important. What about nanobots that we might be able to put inside our body that can go ahead and fix things at the atomic level and help our body? Now, it does sound futuristic, but we are getting there. Okay, they're going to be essential in applications in medicine, communications, solar energy, and the exploration of space. So here's the question. If an atom has a radius of this right here, how many times of these must be lined up in a row to produce a line that's a meter long? Well, this is it right here. Okay, million, billion, so 10 billion atoms would have to be lined up in order to get something a million or 1 meter long. Again, what does that really show? Atoms are extremely small. Okay. The key concepts that you need to know is that democracy, he reasoned that atoms were indivisible and indestructible. And then by using experimental methods, Dalton was able to transform his idea from just that of an atoms to his own theory. Okay. So scientists can observe individual atoms by using instruments such as scanning electron microscopes, or if we just say electron microscopes from now on. Okay, so let's get to the terms. So what's this one? The smallest particle of an element that retains the identity in a chemical reaction. That's going to be an atom. So the second one is, what is the first theory to relate chemical changes to events at the atomic level? And that would be Dalton's atomic theory. Okay, well, that's it for this lecture notes. I'm going to refer you to make sure that you read through the lecture notes again so you can understand, and before you go on to the next assignment. Hey, as always, Nelson out. Go Mohawks.